All right, today we are diving into something truly fascinating. It's a zero-player game that has kept some of the smartest people on the planet hooked for over half a century. We're talking about Conway's Game of Life.
So let's just start with a huge question right off the bat. What if I told you that you could create a universe, a place with things that live and move and build and even compute, all from just four incredibly simple rules? Sounds impossible, right? Well, that's exactly what we're going to explore.
The big idea behind all of this has a name. It's called emergence. You see it all the time in nature. Think about an ant colony. No single ant has the master plan, right? They're all just following very basic rules. But together, wow, they build these complex nests and find food with amazing efficiency. Or think about a snowflake, just simple water molecules, but they come together to form these beautiful, intricate, one-of-a-kind patterns. That's emergence. It's when the whole becomes way, way more than the sum of its parts.
And to really see emergence in action, we have to go back to 1970 and meet a British mathematician named John Horton Conway. See, he wanted to create a little system where simple rules could lead to really interesting, unpredictable stuff. What he came up with was the game of life. And it all comes down to just four rules.
Okay, here they are. It's all about little cells on a grid. Rule number 1, underpopulation. A living cell dies if it has fewer than 2 neighbors. You could say it dies of loneliness. Rule number 2, survival. If a live cell has 2 or 3 neighbors, it's perfect. It survives to the next generation. That's kind of the sweet spot. Rule number 3, overpopulation. A live cell with more than 3 neighbors dies. It just gets too crowded. And finally, and this is the really important one, rule number 4, reproduction. If a dead cell has exactly 3 neighbors, boom, it becomes a live cell. That's it. Those 4 rules get applied to every single cell on the grid, all at once, over and over again.
And just so we're clear, when we say neighbors, we're talking about the 8 cells that are directly touching any given cell. Up, down, left, right, and all the diagonals. That's it. That little neighborhood is the only thing a cell knows about the world. It sounds super simple, but believe me, what comes out of it is anything but. So what happens when you just set an initial pattern and let these rules go? Well, you get this incredible universe of patterns. It's not just random chaos. You get structure. You get things that have predictable behavior. You get things that look an awful lot like life. And these things fall into a few key categories. So the most basic things you'll see are called still lives. They are just stable patterns that, once they form, they never change again. Then you've got oscillators, which are patterns that kind of pulse or blink, cycling through the same shapes over and over. And then you get the ones that really change the game, spaceships. These are patterns that actually move across the grid. Here's a perfect example of a still life. It's called the block. It's just a 2x2 square. Each living cell inside it has exactly 3 neighbors. So, according to the rules, they survive. And all the dead cells around it? None of them have 3 neighbors, so they stay dead. It's in this perfect, stable balance. A little boring maybe, but stable.
Now for a little action. This is a blinker. It's a simple line of 3 cells. In the next step, the 2 end cells die from loneliness, but new cells are born on the sides of the middle one. So it flips from a vertical line to a horizontal line and then back again, forever. It's a simple, perfect little 2-step dance. But this right here changes everything. This is called a glider. It's one of the very first and most important patterns ever discovered. And get this, people found it back in the day without computers, just using graph paper and figuring it out by hand. It's a spaceship made of just 5 little cells, but it does something truly special. And here's the magic. Every 4 generations, the glider completely rebuilds itself, but 1 square over diagonally. It's like a tiny self-propelled machine. It's a little packet of information that can travel across this infinite grid forever, as long as nothing gets in its way. This was a huge discovery. The moment the glider was found, it opened up a whole new universe of possibilities. I mean, if a pattern could move, what else could it do? Could it grow? Could it build things? This is the point where the game of life goes from just being a cool little math toy to something profound. Even Conway himself wasn't sure what was possible. He wondered if maybe every pattern eventually had to either die out completely or get stuck in a stable loop. So he threw down a challenge in Scientific American magazine. He offered $50, which was real money back then, to the first person who could prove that a pattern could grow forever. And you won't believe it, the prize was claimed in just a month.
A team at MIT, led by a guy named Bill Gosper, found this absolute monster of a pattern, the Gosper glider gun. It's this beautiful, complex oscillator that, like clockwork, every 30 generations shoots out a brand new glider. The answer to Conway's question was a resounding yes. Infinite growth was possible. Now, the glider gun turned out to be an even bigger deal than anyone realized, because it meant the game of life was something called Turing complete. Now, that's a pretty technical term, but stick with me because the idea is actually simple. It basically means that this system, with its 4 little rules, is powerful enough to do anything a real computer can do. It can compute.
So how in the world is that possible? Well, if you can create a steady stream of gliders, you can make them crash into each other in very specific ways. And with those collisions, you can build logic gates, the basic and, or, and not gates that are the building blocks of every computer chip. And if you can build logic gates, well, you can build memory and processors. You can literally build a computer. Let that just sink in for a second. You can arrange a pattern of cells that just by following those 4 simple rules acts like a universal computer. This has led to the absolute most mind-bending thing of all. People have actually built patterns that are complex enough to run a simulation of the game of life itself. A universe inside a universe. It's just incredible.
So, okay, besides these amazing nerdy achievements, what's the big picture here? Why are we still so obsessed with this simple game from 1970? Well, it's because it gives us a powerful way to think about our own world.
The game of life is maybe the best example of emergence we've ever found. It proves, without a doubt, that you don't need a master plan or a complex blueprint to get mind-boggling complexity. All you need are simple pieces following simple rules. The complexity literally organizes itself. And this has some really deep philosophical implications. Thinkers like the philosopher Daniel Dennett use the game of life as a powerful analogy. He asks, if a system this simple can create something as complex as a computer, then isn't it possible that the simple deterministic laws of physics in our universe are enough to create something as complex as human consciousness? Which really leaves us with this one last incredible question to think about. Conway's game of life shows us that a universe of nearly infinite complexity can be born from just 4 simple rules. So, what kind of breathtaking, unimaginable things might be emerging right now from the slightly more complicated set of rules that we call the laws of physics?